operate. They've been succeeding in public for more than 15 years now, and yet I think it's really good, so I want to go through some of the main ideas with you. And so the essay starts like this. SpaceX has been remarkably open about how they operate. They've been succeeding in public for more than 15 years now, and yet no one has replicated the results. Competitors know their strategy. The engineering philosophy gets explained in interviews, tweets, and factory tours. Many of the ideas aren't even new. Lockheed's Skunk Works ran similar approaches 60 years ago. Founder Kelly Johnson's 14 rules read like a SpaceX operations manual. The performance gap just keeps getting bigger. In 2025, SpaceX launched more mass to orbit than every other provider on Earth combined. Much more. This is crazy. Every payload from China, Russia, Europe, and all American launchers wasn't even a fifth of what SpaceX put into orbit. They're the only company producing rockets at an industrial scale. A Falcon 9 goes up every 2 to 3 days. Competitors manage single-digit launches per year. The same boosters have been reused 20 times each. The company has sent astronauts to the International Space Station, the first private company to do so. Starlink, their satellite internet constellation, now has over 9,000 satellites in orbit, the largest in history. Both built and launched by the same company. SpaceX is now the most valuable private company on the planet. Yet the skeptics were confident it couldn't happen. Apollo astronauts Neil Armstrong and Gene Cernan testified before Congress against commercial spaceflight. They said that they thought reusability is a dream, and even if it did work, the market was too small to support the hundreds of launches needed to make reusability worth it. Elon was described as a software guy playing with expensive toys. The early failures seemed to confirm them. 3 Falcon 1 explosions between 2006 and 2008. By September 2008, SpaceX had funds for exactly one more attempt, and Tesla was weeks away from bankruptcy. Elon was borrowing money for rent. Then it worked. Flight 4 succeeded, and NASA's $1.6 billion cargo contract followed 6 weeks later. Then came Falcon 9, Dragon, ISS docking, boosters exploding on the pad, boosters landing, crewed flights, and eventually Starship. So is any of this outlier performance repeatable? This is the puzzle. If the strategy is known and the principles are public, what's actually hard to copy? Obvious factors explain some of this, but not enough. And so he goes over some of the factors. The space shuttle retired, creating a gap. This was really good timing for NASA to become SpaceX's biggest customer. But Blue Origin was founded 2 years earlier, and Boeing and Lockheed saw the same opportunity. The grand vision of boots on Mars attracted missionaries, but ambitious visions are cheap, and plenty of founders have them. Elon putting in $100 million bought early runway, but Bezos poured much more into Blue Origin, and legacy primes had multiples of this amount. Technology was also getting better. 3D printing, simulation, advanced materials, all commercially available to competitors. These factors are real and none are sufficient. If they explained it, others could have caught up easily, but they're not even close. SpaceX is a hotbed of case study material. Engineering, product, finance, strategy, manufacturing, product management, etc. If you're interested in the company, these are all important, but I'm more curious about which are repeatable. The question isn't why did SpaceX succeed? That's too vague to be useful. The sharper question, what can someone building hard things actually take away? And so then Max breaks it down into a bunch of subheadings. The first one is the strategy. What SpaceX has done more than anything is minimize the cost of getting things to space. The vision is humanity expanding across our solar system, but the lever is the cost of moving mass from Earth's surface to orbit and beyond. Everything else, the launches, the landings, the reuse, serves that goal. When you study how companies hold advantages over time, consistently being the low-cost provider might be the hardest to maintain. The reason is that it has to be baked into everything you do. It cannot be an initiative or an afterthought. It has to shape how you design products, structure the company, and choose what to build. And as you'll see in the book, it all started from the earliest days. Before starting SpaceX, Elon wanted to get to Mars, but he didn't set out to build a rocket manufacturer. In 2001, he tried buying Russian ICBMs to get there, but the Russians quoted him ridiculous prices. So he famously reframed the question from first principles. What is a rocket made of? Aerospace-grade aluminum alloys, plus some titanium, copper, and carbon fiber. And then I asked, what is the value of those materials on the commodity market? It turned out that the materials cost of a rocket was around 2% of the typical price, which is a crazy ratio for a large mechanical product. 2%. Your car's raw materials are maybe 20 to 30% of the sticker price. Consumer electronics are similar. But rockets, 98 cents of every dollar was going somewhere other than what it was made of. Where was it going? 3 places, it seems. Supplier markup stacking through contract layers, each tier adding 15 to 30% margin. Custom designs that couldn't achieve manufacturing scale. And expendable hardware thrown away after every flight. None of these are the laws of physics. Traditional aerospace treated high costs as fixed constraints. But what if you treated them as variables? How do you actually capture that 98%? I'm reading an early copy of this book called The Book of Elon. It's written by my friend Eric Jorgensen. It'll be out in a few weeks. It's about 200 pages of just Elon in his own words. And he was actually talking about another way to think about this. This is what Elon says from this book. How could the Russians build low-cost rockets? It's not like we drive Russian cars, fly Russian planes, or have Russian kitchen appliances. The US is a pretty competitive place. And we should be able to build a cost-efficient launch vehicle. So back to the essay, another subheading, rethink from first principles. Start with the actual product. If you accept existing solutions, you accept their cost structure. So rebuild from physics instead. Don't ask, what do rockets cost? Ask, what should rockets cost? Elon eventually named this the idiot index, the ratio of the actual cost of a part to the cost of its raw materials. If the ratio is high, he says, you're an idiot. Consider the Falcon 1 actuator. A vendor quoted $120,000 and 18 months of development. SpaceX's engineers built it for $3,900. When founding engineer Tom Mueller's team asked about a critical engine valve, the supplier kind of smirked and left after hearing SpaceX's timeline and budget. Mueller's team made the valve themselves. This pattern repeated across the vehicle. The Dragon's capsule docking mechanism was reinvented from off-the-shelf bike shocks and catalog parts instead of adopting NASA's existing design. There are probably 100 examples like this, most not discussed in public. The philosophy extended to fundamental architecture. SpaceX uses one propellant pair, liquid oxygen and RP-1 kerosene, across all stages. The vacuum Merlin engine uses a fixed nozzle extension instead of a deployable one. This is the main point. Fewer moving parts means fewer failure modes, means lower cost. Compare this to the Atlas V rocket, which uses up to 3 different rocket types in a single vehicle, each optimized for its flight phase. Elon's response to this was, you've just tripled your factory costs and all your operational costs. And so he continues to give examples of how they think and all these little decisions they're making. The Merlin engine family embodies this trade-off. Russian RD-180 engines cost 20 to 25 million each, while the Merlin 1D production runs around $1 million. How? SpaceX eliminated hydrogen's complexity by using kerosene, used regenerative cooling with the fuel itself, and optimized for manufacturability over maximum performance. The result was 95% of theoretical efficiency for 80% cost reduction. Merlin's performance is slightly lower, but good enough at 1/20th the cost. But identifying where to cut costs doesn't mean you can actually cut them. You still have to build the parts. Once SpaceX concluded that atoms were cheap and process was expensive, vertical integration followed almost inevitably. That's a great line. SpaceX concluded that atoms were cheap and process was expensive, and so therefore vertical integration followed almost inevitably. The next subheading talks about this, becoming your own supplier. If materials are cheap and the tax is all process and overhead, you need to control the process to capture the savings. You cannot negotiate your way to a 10x cost reduction with suppliers who have profits baked in at every tier. So SpaceX became its own supplier. By building 80% of its hardware internally, engines, structures, avionics, software, and key ground systems, SpaceX collapsed the traditional aerospace stack. They outsource raw materials and commodity parts and make everything else themselves. That's something SpaceX didn't originally set out to do, one engineer noted, but was driven by suppliers' high prices. This wasn't an ideological commitment to doing everything in-house. It was the result of suppliers repeatedly quoting prices and timelines incompatible with SpaceX's cost targets. The benefits compound. When several tiers each add 15% margin, total cost multiplies through the layers. A NASA study found SpaceX developed Falcon 9 for roughly $440 million. They estimated the same work with traditional contractors would have cost 3 to 10 times that amount. Vertical integration also accelerates iteration. Another great line. Vertical integration also accelerates iteration. When an engineer needs to change a bracket, weld, or circuit board, the manufacturing engineer is in the same building, using the same CAD systems and tooling. Materials, jigs, and processes can evolve together on the scale of weeks, enabling a rapid progression from Falcon 1 to successive Falcon 9 variants, each iteration improving performance and reducing cost without waiting for suppliers to retool on multi-year cycles. But vertical integration creates a new problem. It concentrates fixed costs. If you own the factory, the machines, and the staff, you're losing money every second they aren't building something. At the traditional launch cadence of 2 to 4 vehicles per year, in-house manufacturing is a liability, not an advantage. To make the math work, you need volume. Before we get back into this, I want to tell you about the presenting sponsor of this podcast, Ramp. One of the main themes in the history of SpaceX is constantly attacking and questioning your costs. Ramp helps many of the most innovative businesses in the world do exactly that. The median company running on Ramp cuts their expenses by 5%. And just like SpaceX has demonstrated, a religious dedication to controlling costs helps increase revenue and pursue opportunities you couldn't otherwise. We see that in the Ramp data too. The median company running on Ramp also grows their revenue by 16%. Many of the top founders and CEOs I know run their business on Ramp. I run my business on Ramp, and you should too. Go to ramp.com today to learn how they can help your business save time and money. That is ramp.com. So that brings us to the next subheading, build a platform. The only way to get volume is to standardize. Build a common platform that customers have to adapt to. The existing approach was bespoke vehicles per mission, custom adapters, mission-specific modifications, multiple vehicle families. This optimizes each mission at the expense of manufacturing scale. SpaceX bet the opposite, that cost savings from standardization would exceed the value of customization. Yes, customers wanted custom solutions, but they wanted low prices even more. Force them to choose and they will adapt. The Falcon 9 became the industry's Model T, one rocket built in volume. Same 9 Merlin engines on the first stage, same vacuum Merlin on the second. Same structures, same diameter, same aluminum, lithium alloy, same welding methods, same avionics, same ground systems. Even Falcon Heavy is just 3 Falcon 9 first stages strapped together with a shared upper stage. A scaled variant from the same core, not a new vehicle. SpaceX published a Falcon user's guide which defined bolt circles, electrical connectors, and fairing environments. Customers designed to SpaceX's spec instead of demanding customizations. Satellite orbits adjusted to Falcon performance curves. This flipped the negotiating power. Instead of aerospace companies serving satellite specifications, satellites adapted to SpaceX capabilities. The economics of manufacturing is what makes this work. Building 40 identical Falcon 9s annually creates automotive-style learning curves that are impossible in custom aerospace. As production scales, learning improves and cost declines. How this worked in practice is that every anomaly, wear pattern, or manufacturing defect fed back directly to the teams that design the parts. Finally, there's the logical conclusion of standardization, which is reusability. Reusable boosters are still the same Falcon 9 cores. You aren't just building the same model of rocket, you are literally flying the exact same hardware. Because every booster was identical, every landing attempt provided perfectly comparable data. If making 40 rockets creates a manufacturing learning curve, flying the same rocket 20 times creates an operational learning curve that's even steeper. The economics are devastating for competitors. Traditional providers launching a handful of custom vehicles per year never accumulate enough data to even start this cycle. And this is so good how Max ties this all together. You can probably see why all 3 tactics were necessary. First principles identified the waste. Vertical integration provided the control to eliminate it. Standardization allowed the volume to make that control profitable. Without all 3, the system breaks. They work together so that each flight makes the next one cheaper. What does this sound like? A flywheel. Lower costs enable lower prices, which capture market share, which increases volume, which drives costs lower still. The incumbents understood this too late. They optimized